Hello, this is part 3 of my mini lecture of exponential growth and decay. Part 1 was to just kind of give you a general overview of the idea of what an exponential growth and decay is. And then on this one, I gave you an exponential decay. My last part, my part 2, was exponential growth. So this will be the final part of the series. But this one's an exponential decay type problem. And remember from part 1 that k will be negative in these types of problems. And the substance that I'm referring to as is kind of a make-believe substance I just kind of made up. So a half-life of a substance, I call it substance A, is 2,500 years. Now let's understand what that really means. It takes 2,500 years for whatever it is, how much the substance is right now, to half itself. So for example, if you have 80 grams, it's going to take you 2,500 years to go from 80 down to 40. So that's the half-life. So once you've got that, it's going to take another 2,500 years after that to go from 40 down to 20. And then down to 20, it's going to take another 2,500 years to go from 20 down to 10. And then another 2,500 years to go from 10 down to 5. So as you can figure this out, you nearly never get to 0. You get close. You go from 80 to 40 to 20, and then 2,500 years after every time you do that. So 80, 40, 20, 10, 5, then 2.5 grams, and then 1.25 grams. You keep halving itself, you never really go to 0. So you always have a little bit there, okay? But this one has a very slow decay rate, as you can probably imagine, because it takes 2,500 years just to go from 80 down to 40. So it's going to take 5,000 years to go from basically 80 down to 20, because it goes 80, then 40, then 20. So what I'm trying to do is how much is going to be present in 25 years? Just 25 years. That's all I want. Well, how much is going to be in 25 years? But here's I put this problem on for a reason. The 25 years, I know it's 1/100th of this. It's you divide 2,500 by 25, you get 1/100th, and then people will take 1/100th of 80 and figure out that's what that should be, but that's not the way it works. Okay, so what you have, because what happens is you have a lot at the beginning, and it slowly goes down. It's not linear reductions. If it was a linear reduction, that would be the concept. That's how you would kind of do it. But this has a lot at the beginning, and then it kind of slowly comes down and it flattens out a little bit. So what you have to do is remember to figure out the initial amount, which you know is 80, and you got to figure out what the decay rate is. I never told you what the decay rate is. That's what we got to figure out first. So you have 80 to begin with, and this time you go down from 80 down to 40. And it takes 2,500 years for that to happen. So if you notice in this formula, I know everything except for the k. So I divide by 80. So 40 by 80 is 0.5 equals e to the 2,500k. But do notice that the n is less than what I started out with, and that makes sense because it's decaying. So on my part 2, remember that was a 2 over there. On part 2 was the one that's doing the growth ones. The decay ones are going to be 0.5. So if this one was, it really didn't really matter what that number was. If this was like 120, then this number would be 60. If this number was 200, then this number would be 100, because it's got to be half of it when you're dealing with half-life. And it takes 2,500 years for that to happen. So again, you're going to need to pull out the calculator in a second, so you might want to get that ready. So it'll be the natural log of 0.5 equals the natural log of e to the 2,500k. And then when you do the math, k is equals to the natural log of 0.5 divided by 2,500 when it's all said and done. And again, you need a 4 decimal approximation for that one. So I'll need to get my calculator out as well. And here mine is. So the natural log of 0.5, of course you got to turn the calculator on first. That always helps. Natural log of 0.5 divided by 2,500, and that is equals to very small. It's negative 0.0030 zeros, and then I'm going to round this number to a 28. So it's negative 0.00028. Now, when you get numbers like this, people think they've made a mistake, and they really didn't. you got to understand, it takes 2,500 years to go from 80 down to 40. So it's decaying very slowly. And when that happens, it's almost zero. So it's not very much at all. If this number was like negative 0.2 or negative 0.3, then it wouldn't take 2,500 years. It would probably take less than a year to have itself. So, and but anyway, that's why it's so low. So now that you found that number out, you just plug that back into your main formula. So n is equals to 80, what you begin with, e to the negative 0.00028. And I rounded that up, actually. It was like 277, I think is what it was on my calculator, times t. Now, some of the easier problems, okay, will ask you, or tell you what how much was going to be in a certain amount of years, and this is one of them, because what they want is how much will be present in 25 years. Okay, so this time it is an easier one. So all you got to do is plug 25 back in for the t. So it's 80 times e to the negative 0.00028 times 25. And you got to do the math on your calculator. The thing about this one you have to be careful with is plug it into the calculator correctly. A lot of people get all the work done but don't know how to use their own calculator. And it's really frustrating for you and for me, actually, because I see that you did all the work correctly, and then you get from here, and then the next step is wrong because you didn't put the numbers into the calculator correctly. So you got to be very careful how you do that. I'm going to show you how most calculators will work. If you can get that on your screen and then hit enter, you're probably going to get the right answer. Okay, it's just a lot of people will not put the parentheses on this right there. Now some calculators will fix that for you because they automatically put it in there for you. But if you don't have that, if you don't put parentheses around that, the calculator is going to take e to this power right here at negative 0.0028, multiply that by 80, then at the very end multiply by 25, and you don't want to do that. You want the decimal negative 0.00028 to be multiplied by the 25. So the parentheses, it's got to surround that. So that's very important. But like I said, most calculators they've learned to do that. So if you have like an older model that doesn't put the parentheses there, you got to remember to put it there yourself. So let me put that in there. So it's 80 times, okay, natural log e to the power of, so shift natural log, and then negative 0.00028 times 25. And I get 79.44. Now, before I go much farther and talk to you a little bit about the answer, the negative right here is not the minus sign. It's not the plus minus times. It's not the ones on the right side of your calculator. It's not that one right there. It's the one that says a minus, and it's usually right below the 3 on a lot of the TIs anyway. So, but it's a negative. It's not a minus sign. So if you put minus, the one that's right above the plus, then you're going to get a syntax error or some kind of math error or something like that. And so it's that's a negative, not a minus. I know in our math world we kind of treat those as the same thing. And but anyway, it's not the same thing for the calculator. Anyway, so my answer is 79.44 grams. Yeah, I'm using grams. Now, if you recall, I started out at 80. I had 80 to begin with, and I'm down to 79.44. So I've really lost just half of a gram, half of 1 gram, and it was 25 years in the process of doing that. Well, why is it so low? Is because the decay rate was so low. It takes 2,500 years just to go from 80 down to 40. So I would have expected this number to be in the 79 range. So if you would have got 60 grams here, I would have been, well, wait a minute now. It takes you 25 years to go from, 80 down to 60. And it takes 2,500 years to go from 80 down to 40. So your math is all wrong on that one. So I would suspected this number would have been pretty high, but below 80 though. So, but anyway, this is part 3 of 3 of the exponential growth and decay models. And now, just as a summary now, remember, both formulas the growth and decay uses the same one. And the distinguishment between the two is the K is positive. If it's a positive number, it's growth. And when K is a negative, it's decay. So if I just threw a problem at you and say, okay, here's a exponential uninhibited problem. And you would say, well, which one is it? Well, I'll just look at the K. If it's positive, I know it's growing. If its K is negative, I know it's decaying. So you don't really even have to be told one way or the other. It's just by that number right there. Okay, and one thing I haven't explained on these three-part series is the word uninhibited. Uninhibited basically means nothing is affecting it other than time. So when bacteria grows, you know, antibiotics kill bacteria. So if you put antibiotics within bacteria, then it's inhibited. Okay, you want it to be uninhibited growing. So so basically, uninhibited basically means there's no external factors that is affecting that growing or decaying other than time. That's all it means, uninhibited growth. So, but anyway, that is 6.8, part 3 of 3. I hope this helps. This is it.